All right, let's get started. Thanks to all for coming. I know it's an unusual time for the seminar, so very pleased to have Jonathan Mosheiff, who tells us about weight distribution, the distribution of weight distribution, random linear codes, and joint work with Natalie.
Okay, thanks. Okay, so I have the next slide here actually explains what's a code. So it might be a bit unnecessary, but let's just say it for the sake of it. I don't know whether it's necessary. Okay, great. So a binary code is just a subset C of the binary hypercube f2 to the n. Okay? And basically, the reason that we want these is that suppose Alice wants to send a message X to Bob, and Bob gets some noised message. So he gets some X plus some noise vector. Then if that noise brings us to some point, to this red point here, then when Bob gets this message, he can just say, OK, let's look for the closest glue point, the closest point actually in the code. That might be what Alice has sent, and he fixes it to that closest point, and then he manages to recover X back again. So what we want from this code is, in one hand, we want the points in the code to be far from each other to allow for correction. And on the other hand, we want it to be as big as possible, which allows us to get a good rate of communication. And of course, these two notions are at odds with each other. And this is pretty much like the entire trade-off that we have in codes. OK. So we're going to talk specifically about a specific construction of codes, one of the most basic constructions of codes, which is that of random linear codes. So what's a random linear code? I just want to take my code to be some random subspace, some random linear subspace of f2 to the n. So what's a way to generate a random linear subspace of f2 to the n? So I fix some lambda, which is going to be my the relative codimension of my code. And I choose a bit matrix of size lambda n by lambda. And then I just take my code to be the kernel of this matrix. OK, so really, almost surely, we're just going to get something with dimension. I mean, it's possible that we get something with dimension slightly larger than 1 minus lambda n, but almost surely the dimension is 1 minus lambda n. And a code, and this is what we're going to call this C. This random C is what we're going to call a random linear code, given this lambda. OK. And these codes are like, pretty much one of the earliest things that people have done with codes is construct these. And in the Shannon paradigm, these are known to be, OK, so these give you optimal rate distance trade-off for random errors. And if you assume that the errors are adversarial, that someone is intentionally trying to prevent Bob and Alice from communicating, so they put the errors exactly on the most important bits, then these codes are still the best, give you the best known trade-off today. We don't know the exact trade-off in this case, but we know that this is the best we know how to do today. So these are like so these codes are very important and basic, and we'd like to investigate them. We'd like to investigate what they look like. Okay, so most of the interesting properties of a code can be deduced from what's called the weight vector of a code. So what's a weight vector? So given the C, we're interested in this vector WH to WN, in which WI just tells you how many vectors in the code are of specific Hamming weight I. OK, so we just define Li to be the ith layer of the hypercube, and then we take Wi to be the size of the intersection of the code with this layer. Okay? And we're going to try and study the weight code of this random linear graph. So more concretely, we're going to fix, OK, so we already fixed this lambda before. We're also going to fix some gamma. OK, it says by mistake that gamma is between 0 and 1. It should be between 0 and half. And we take a random linear code, again, as we described before. OK. And we're going to define the random variable x to be w of gamma n. So we're looking at specifically at one element of this weight vector. That's the number of elements of the code that have weight exactly gamma n for some constant gamma. And we'd like to see what's the distribution of this random variable x. OK. And OK, so what I'd love to tell you is what's the distribution of x. And even what I'd even love to tell you more would be what's the distribution of the entire weight vector together. And what I'm going to tell you is what are the central moments of this x. OK, so you're not going to have a clear idea in your head of how exactly this distribution looks like. We're just going to compute these moments, and I see this is probably the first step in actually understanding the distribution of these weight vectors. OK. So let's see how to. I mean, before I state the result, I want to play with this a bit. So let's play with this x. So let's start by computing its expectation. Okay? So computing its expectation is very easy. You're just going to look at x as some sum of indicator variables. So we have the gamma nth layer. And for each element of the layer, we define an indicator yu. And we know that x is just the sum of all these yus. And then we can just, OK, so the expectation is just, we know what's the probability that a certain yu belongs to the code. Okay? A certain u belongs to the code because every vector of the hypercube has the same probability, except for the 0 vector. Every vector in the hypercube has the same probability of belonging to the code, and that probability is exactly 2 to the minus lambda n. So just to make the notation easier, we're going to set big N to be this, and then we're going to say that the probability that a certain vector belongs to the code is big N to the minus lambda. Okay, and then we get this expectation of x, which is n to the h of gamma minus lambda. Oh wait, let's just say let's just say a bit more slowly what's going on here. So the size of the layer is n over gamma n, and then we can approximate n over gamma n as big N to the entropy. H of gamma is just the entropy of a random variable that's distributed gamma and like 0 probability, 1 minus gamma, and 1 probability gamma. Okay, so this is just a good approximation for n over gamma n. OK. By the way, I don't know how this usually works. Just in Israel, people tend to be very rude, so they just bother me all the time when I give talks, and I kind of got used to it. So really feel free to bother me. I don't know, like if you have any question or something, so just go ahead. OK. OK. So that's the expectation, and from now on we're going to limit ourselves to the case where this expectation tends to infinity. Okay. So you can see here that this expectation can tend to either so gamma and lambda are constants. So when you have this exponent h of gamma minus lambda, so the distribution when n becomes large, this distribution can tend to either infinity or to 0. So we're going to focus right now on the case where the expectation goes to infinity. This seems to be actually after my work with Venkat yesterday, I can tell you this, the behavior is dramatically different between these two cases, and I think the richer case is probably the case we're talking about, where h of gamma is larger than lambda, and then the expectation goes to infinity. Okay, so that's what we're going to assume from now. Okay, so let's now do the variance. This is still going to be easy. So in order to do the variance, I'm just going to need this very basic proposition, which says the following. So now, okay, so before we said that the probability that a given vector belongs to our code is 2 to the minus lambda n. Now, what's the probability that a set of vectors, some finite set of vectors, are all contained inside the code? So our code is linear. So for a set, so a set being contained in the code is equivalent to the subspace spanned by that set being contained in the code, right? It's exactly the same thing. And the probability that our code contains a certain subspace, it's just 2 to the minus n 2 to the minus n lambda times the dimension of that subspace. Okay, you can just think of it as, in order to contain a subspace, you just need to contain the elements of, like, all the elements of its basis, and the elements of this basis being contained in the kernels of some random matrix. This is just independent of each other. So we get that. So in order to know what's the probability that a group is contained in that a set is contained in the code, we just need to take n to the minus lambda and take it to and exponentiate it by d. Okay, and it's nice. It means that basically variables, like, okay, so vectors being linearly independent means that their indicator random variables are independent as random variables. Okay, that's basically what this proposition means. And now we can use this to compute the variance. So how does this let us compute the variance? The variance is this sum of the variance of yu plus the sum of the covariance of yu and yv over different y and v. And now we know that this covariance is, okay, so we're talking about the covariance of yu and yv, where u and v are different. Now, if u and v are different and they're both non-zero because they both belong to the layer, so they're not the zero vector, then they're also linearly independent of each other. And if they're linearly independent of each other, then they are also independent as random variables, so their covariance is 0. Okay, which is why this vanishes, and we get the variance of n to h of gamma minus lambda. Okay, up to now it was easy. Now let's see what we do when we want to compute a general kth moment of this variable. Okay. So let's start with plane moments. I said that we're going to compute centralized moments, but let's start with the plane moments for a minute. Okay, so what's a plane moment? The plane moment of the kth plane moment of x is just sum over tuples of the product of these yui's, right? I'm summing over all k tuples of vectors, and I'm asking what's the probability that all of them together are contained in my code. And I want a nice way to count these things. Okay, so one basic manipulation is just that if I have an element of the above sum, u1 to uk, I'm going to write this k tuple as a matrix. Okay, so I have a matrix where all of these, so each row is one of these ui's. So I have k rows, okay, and I have n columns, okay, and I'm summing over all the tuples over tuples of vectors where every vector must belong to the layer L gamma n. So each row of this matrix has the same weight, gamma n. Okay? So in order to sum over tuples, I just need to sum over matrices that satisfy this row condition. The row condition is just what how I call every row being of weight gamma n. I sum over all of these matrices. And now here for each tuple, I took this is just the probability that all of these ui's belong to my code. Okay? And this probability, as we said before, is exponential in the dimension spanned by these vectors, which is that the rank of this matrix. Okay, so what I'm basically doing is I'm summing over matrices, and I'm taking n to the minus lambda times the rank of my matrix. And this is pretty much what I need to compute. Okay. So now in order to make my life a bit easier, I'm going to want to, okay, so summing over all matrices. How do I do that? Well, we're going to classify our matrices according to their column space. Okay? So I just take this sum and I think of it as a sum over, instead of taking the sum over all matrices, I take a sum over all possible column spaces here. Okay, and for each column space, I sum over all the matrices that have this specific column space. So what does this mean? So think, for example, of me like, okay, I can, for example, take the set of, let's say, give an example here. Okay, so suppose, for example, I can think of summing over only matrices in which every column is either 1, 1, 1, 1, 1, or 0, 0, 0, 0, 0. In other words, I can think of the set of all matrices in which all the rows are identical to each other. Okay, so these matrices are in this sum we're taking as if I take here U to be the space, the subspace of F2 to the K, okay, the column space in which I only have the vectors 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, then here I sum, okay, so I consider this term that corresponds to this U, and then I get here a sum over all matrices that I just described, all matrices in which each column is 0, 0, 0, 1, 1, 1. So these are all matrices belonging to this specific column space, okay? So this is just this classification, which is going to help us. And specifically, yeah, this is, okay, this approximation is due to a small lie that I'm giving here. So if I really want to classify matrices according to their column space, then what I really need to do is ask that the rows of the matrix, that the columns of the matrix really span this U that I'm summing over here. And instead of asking for that, I'm just asking that each column belong to U. So in theory, for example, when I want to sum over matrices whose column space is 0, 0, 0, and 1, 1, 1, I also count the matrix in which, just the 0 matrix, whose column space is not this, right, is not 0, 0, and 1, 1, 1. It's actually counted twice, once for this U and once for the U, which is all zeros. And this is why, I mean, this is really negligible, but this is why the approximation symbol is here, okay?
So one comment is that, so it is still an upper bound, right? But the point is you're interested not just in an upper bound, but like...
Yeah, it's an upper bound, but it's actually a very, very good estimation. Yeah. Okay. And now I can just say, okay, but all the matrices, okay, the matrices with this specific column space are pretty much just all have the same rank, okay, because we all have the rank of that given column space. So instead of taking rank A here, I can take the dimension of U, and then I just find myself looking at this sum, which is what we're going to compute. So what's this sum? We're summing over all linear subspaces of F2 to the K. Okay, so in order to compute the Kth moment, looking at all subspaces of F2 to the K. And for each such subspace, I need to take this constant n2, which is n to the minus lambda dimension of U. Okay, so I'm taking something which is exponentially decreasing in the dimension of U. And I'm multiplying it by the number of matrices which satisfy both conditions here. Okay, so I'm trying to count matrices which have rows of weight gamma n and columns contained in this U. And this is going to be the type of thing that we're actually going to have to compute here. Okay. So now again, I said that we're going to compute centralized moments. So what happens to this expression when we centralized? So actually, something really nice happens here. So in order to explain what happens, let's for a minute compare our situation to that of a random, just a random code. Okay, so instead of taking a random linear code, we can also just take an even more basic construct, which is that of just a regular random code. Okay, so in a regular random code, I look at the elements of F2 to the n. I actually forget about the structure of F2 to the n and just remember that it's a bunch of elements. And I take each element with some probability p, which is, let's say it's 2 to the minus lambda n. Okay, so that the expected number of elements in my code would be the same as the one in my linear code C here. Okay? So what happens if I take such a code and then I want to compute again the moments of its weight vector? Then it's going to be very easy. Why is it going to be very easy? Because this x would then just be a binomial variable. It's going to be a binomial variable because now I have these n over gamma n elements, and out of which I take h1 with this probability p, right? Okay. So what would happen if I try to compute this e of x to the k in the binomial case? Okay, in the case of just a random nonlinear code, just a regular random code. If I try to compute this and did this kind of classification, then I'd actually do something that's very similar to what they do in one of the proofs of the central limit theorem. Okay, in the central limit theorem, they look at tuple, like you want to compute the, the moments of, what they do is they computed the moments of a binomial distribution with high n in order to show that they're the same. Like you compute these moments and then you see that it's the same moments as those as a normal distribution. So you also want to classify these tuples. Now, how would you classify tuples of, you have sums of independent variables. So how do you classify these tuples? The only natural way to classify is according to repetitions of a variable inside the tuple. Okay, so you say, okay, so I have tuples in which I have 3 of this and 4 of this times 4 of this, this to the 3 times this to the 4 times this to the 2, okay, and so on and so on. And then in the way that the proof of the way that this computation goes is that you say the following: if you centralize your variable, then tuples in which a variable appears only once vanish. Why is that? Because if I have some, expectation of x to the something times y to the something times z, where z appears only once, then after centralization, the expectation of z is 0. And because it's independent of the others, I just multiplied, to get the influence of the tuple, I just multiply everything by the expectation of z, so I get a 0, so it vanishes. Okay? Now, we're going to get a similar phenomena here. So we're also going to get when we centralize, some of these random subspaces, some of these subspaces of f to the decay are going to vanish. So which ones are these going to be? These are going to be those in which we have some coordinate which has no interaction with the others. Okay? If we have some coordinate which has no interaction with the other coordinates, then it would be like that variable which only appears once in a tuple and has no connection to all the other variables. Okay, so we say that a linear space U in a sum is robust if it's defined by linear equations that care about every coordinate. Okay, so for example, if I'm defined by x1 plus x2 plus x3 equals 0, and x3 plus x4 plus x5 equals 0, and I only have 5 coordinates, when I just had equations that somehow say something about every coordinate. So this is a robust space. Now, what does it mean to be non-robust? Being non-robust means that some coordinate does not appear in any equation that defines me. And this means that this equation can be whatever it wants, this coordinate can be whatever it wants, no matter what the other coordinates are. So this exactly means that when I centralize, I get a 0 for such tuples. Okay? So I'm only left with the robust spaces here. And notably, one of the spaces that I just threw away is the space, it's just the space u equals f2 to the k, okay, which is just when I take k coordinates, when I just look at k vectors which have absolutely no connection to each other, no constraints limiting them at all. So I just threw this one away, for example. Okay, so this is the kind of expression that we have. And just to understand what kind of work needs to be done now, so note that, so we have a sum over certain subspaces of f2 to the k. And we have this n to the minus lambda dimension of u, which decreases exponentially as we increase u in the terms of giving it making it larger, which increases its dimension. So this term is going to decrease. But on the other hand, the number of matrices which I'm counting, which have to have their columns belong to u, are now less constrained. So this tu is going to increase. So the kind of work that we're going to need to do is to find out which u actually dominates this term. And this is very meaningful to understand. I mean, besides the fact that it helps compute the moment, it actually tells us something about understanding which u dominates this sum. Actually helps us understand what does this behave like, because it explains to us what kind of okay, so saying which are the tuples that mostly define the behavior of this sum. Okay, you can say something like, oh, this sum is mostly this moment is mostly influenced by k, like tuples of k vectors which all sum to 0 together. Or I couldn't say, okay, this actually is mostly influenced by tuples of k vectors in which the first 3 are of sum 0, and then the first and the fourth one are similar, and so on. Okay, and it would say something about the behavior of this thing. Okay, and we're actually going to show that there are only 2 candidates for who dominates this sum. And the 2 candidates depend on what are k and gamma and lambda, okay, which are my 3 parameters. So the layer I'm looking at, the density of the rate of my code, and the order of the moment I'm trying to compute. And these 2 candidates, this is like 2 different extremes. So one extreme would be the vectors in which just u1 and u2 are the same, u3 and u4 are the same, like matrices like this. So this just corresponds again to the term that dominates in the case of just a binomial distribution again. In the binomial distribution case, after I see that all tuples in which a variable appears just once vanish, then I see that the type of tuple that's left dominating is when I take tuples of size k in which k over 2 variables appear each twice. Okay, so this is exactly the type of spaces that can dominate here as well. And actually, when these spaces dominate, that means that our x really behave just as if it was a binomial variable, which means that for the sake of moments for which this is the dominant space, it means that the fact that we took a linear random code has no effect. It actually just behaves as if we just took some regular random code, just a plain random code, which is in some sense very nice, because it means it's easy we really understand these codes very well if that's the case, if linearity doesn't really matter in these cases. Okay? Now, the other candidate for domination, which dominates some other spectrum of parameters, I'm soon going to tell you where each dominates, is the other extreme. This is the space of even parity vectors in F2 to the k. And this means that I'm now looking at matrices of k vectors all in the gamma nth layer, where the sum of the k vectors is 0. And this is the only relation that I'm going to require on these vectors. So for example, if k, just to make it concrete, so if k equals 3, then I'm just saying that if this dominates, then I'm just saying that x is mostly influenced by the fact that I sometimes, if I have two vectors and they happen to both belong to the code, and their sum, okay, and their sum happens to also belong to the gamma nth layer, then their sum also belongs to the code. Okay, that's what it means for this to be the dominant type of term. Okay, it just means that this effect that I just described of the sum of 2 vectors in the same layer also belonging to the same layer. So if these 2 belong to the code, then the third one also belongs to the code. That's the main influence on what our x looks like. And this is obviously very different from the case of a plain random code. Yes?
Why does the first one not also satisfy the second one?
I'm sorry?
Why does the first class not also satisfy the second condition?
No, it satisfies the second condition, but also it's much more strict. I mean, okay, it's the space defined by the first the space defined by the first set of equations is has a much smaller dimension, so it's less penalized in that n to the minus lambda d mu. Okay. Okay. So now that I told you this, I can actually say what's a result. Okay, so ignore all the top 2 rows for a second, the top 2 lines, and just look at this. Okay. There is some k0 which depends only on gamma and lambda, okay, such that up to that k0, okay, so the moments behave one way up to k0 and another way from k0 and on. Up to k0, the moment, okay, so what I did here was normalize the moment by its variance so that you can see exactly what it looks like. So basically it's going to be k semi-factorial for even k and 0 for odd k. And this should probably look familiar to most of you. This is just the moments of a normal distribution. Okay? So up to a certain k0, our x has the same moments as those of a normal distribution, and this is exactly up to that k0. It's exactly that, this type of the identical pairs spaces that dominate. Afterwards, we get a different behavior from that k0 and on, and then we get then we get this behavior, which is not understandable yet because it includes this function big F. And what I can say is that the moments start growing much faster than those of a normal distribution at this point. Okay, so suddenly the fact that we're working in a linear with a linear space suddenly takes effect, and then the moments start being more biased and grow very quickly. So this is similar to a normal distribution. And here, I just need to say, okay, so what's going on here? This is just some function which we have this explicit description for. And I'm not going to, you're not going to fully understand what this function means, and I'll just try to give you a basic idea of where it comes from. So this is the, this is the entropy of some distribution, this fk gamma. And yeah, probably the most important thing to say about it is that, so this grows super linearly, which means that these moments grow faster than exponentially in k. And this is part of the reason why we don't have, even though we actually computed the moments, we don't have a clear idea of the distribution. Because using, so how do you usually go about, after you compute the moments, how do you usually go about computing the distribution? So one way to do it would be find some other distribution with the same moments, and then use moment convergence theorems to show that they have to be the same distribution. And in this case, this can't work because the moments go to infinity. Okay. So this is our main result here, and just I said that we have this k0, which is the threshold that up to k0 we have this one behavior, this behavior similar to a normal distribution, and after k0 we have behavior which is much more in which the moments start growing much quicker. So what does this k0? How does it actually behave? So this is just the this is our this axis represents gamma and this axis represents lambda. So I said that k0 depends on both gamma and lambda. So how does it depend on them? First, this blue line is just indicates that we only care about the cases where lambda is less than h of gamma, which is why we limit ourselves to below this blue line. So you can just say that in this whole very big area, k0 is already 3. And then here it's 4, and then only here it's even larger than 4. It very quickly, if I also added the lines for k0 equals 5, and so you can see that it's very, very small on most of our, in most of the parameter space. And this means that basically it's already on the third moment that we stop behaving like a normal distribution in a very large set of parameters. Okay. So let's talk a bit about how we actually we actually do this computation. Okay. So as I said, the basic thing we need to do is to count these matrices satisfying the two conditions. So we're looking for matrices that satisfy the row condition, which means that, okay, we want k by n matrices, where every row has the same weight gamma n, and every column okay, wait, I should have said something before, I'm sorry. We're going to estimate now T of vk. So what is T of vk? Okay, we wanted to compute in general the matrices in which all the rows have weight gamma n and the columns all belong to a certain column vector, to a certain column space. Okay, so in order to do that, we're going to start with just the simplest non-trivial column space. And that's just the space of even vectors. Okay, that's actually the space that we said that dominates starting from k0 and so on. Okay, so we're first going to just count the matrices satisfying these two conditions, and later we're going to show that Tu. Okay, so the matrices satisfying this condition for every vector space can be somehow expressed or bounded by these elements, just by the case of even parity columns. Okay, so just let's consider this problem for now. So you want matrices with rows of weight gamma n and even columns. And you can even just think about how to do it for the basic case, which is k equals 3. So for k equals 3, it's quite easy because you have, so how do you build such a matrix? So you know that the columns have to be taken from these four types because you only have even columns. And now it's just, the question is that it's just how many ways are there to arrange columns of these types such that each each row gets to have weight gamma n. So this actually yields a set of equations because we know that, okay, so the number of columns in general needs to be n. Okay, so this is the first equation. And also we get these three equations which say that, so A3 plus A4 is the number of columns that have 1 in the first row, so this needs to be gamma n. And the same for the other two pairs, so that's, okay, so that we also get this, in the second and the third row we also get some gamma n. So these are 4 equations in 4 variables, so we can actually solve them, and then we know that the number of such matrices is exactly this multinomial variable, and we're fine. Okay, so this makes us a bit optimistic about this computation. And the problem is that now when we try to generalize it for some general k, okay, so we're looking at k rows and n columns, and we have k rows, and we have 2 to the k minus 1 variables. Why do we have 2 to the k minus 1 variables? Because our variables are how many appearances do we have of every column which is even. Okay, so a k bit, we're looking at even k bit columns, so we have 2 to the k minus 1 of these. And then we don't have one solution for these equations. We have an exponential number of solutions to these equations. And each such solution yields a multinomial variable. Okay? So to compute this precisely, we need to sum over all solutions to all exponential number of solutions to these equations, and take the multinomial variable for each of them. And the best that we actually know how to do is to just estimate that, just take the solution that maximizes the solution to the equations that maximize this multinomial variables and take this as some reasonable estimation. And the problem is that this gives a double exponential error because the number of solutions that these you have 2 to the k variables, so the number of solutions that you have is double exponential in k. So this is pretty bad. So we also have another approach, which is the one we actually use in the paper. And this approach is different. What we say there is the following. Let's try to just randomly construct these matrices in some way. So how are we going to generate? Okay, so you want to generate a k by n matrix where, okay, so you know that the columns have to be even, and you want the rows to all have weight gamma n. So the way we tried to do this for a while was by just try to somehow put the columns randomly in some way. But of course, if you're going to just try to throw random columns which are even, then the probability that you're going to get gamma n weight in each row is very, very small, and thus also kind of hard to compute to the precision that we need. So instead, we're still randomly taking columns, but we take it from some distribution which makes it pretty likely that we're going to get the type of matrix that we need. So we define some distribution P, which is first, it's supported by even weight vectors, so that the columns are all of even weight. And we also made sure that the expected number of ones in every row of the matrix is going to be gamma n. Okay? So now there are many distributions with these properties. So if you try to think of how do you construct a distribution with these properties, so you just solve linear equations, right? Because you have the probability of each. It's actually exactly the same linear equations that I described to you before. You just solve these equations, then that say that you have what's the probability of each column vector, and you have many ways to decide what are these probabilities going to be, and the expectations of the rows are going to be linear in this set of probabilities. So, which of all these p's did we take? We took some p. We took the p out of all of these, which is of maximal entropy. Okay? So there's a very rich theory of entropy maximization. And the basic problem that entropy maximization tries to solve is exactly this. Okay, so it's just you want a distribution supported on a certain set. In this case, this is our even vectors, and you want and you have certain conditions. You want the expectations of certain functions on your random variable to be something. Okay. So these are exactly the type of conditions that we have in 2 here. And then it is known that there is a unique distribution which is of this form for some alpha. Okay? And there's a unique alpha which satisfies, for which if you define this distribution like this, then you're going to get a solution for your, you're going to get a solution for your equations here in 2. Okay? So we just said, okay, so take this alpha for which the alpha for which this 2 holds. As you can see, what does this basically mean? It just means that we give each column vector a weight which is exponential in its we give it some alpha to the u, something exponential in its weight, and then we normalize this to get a probability distribution. Okay, and the distribution like this, which satisfies 2, has maximal entropy, and we took that distribution.
So is alpha more than 1 here?
That's alpha, since gamma, okay, so alpha is 1 when gamma is half. So since we're looking at gamma less than half, then alpha here is less than 1.
You want to favor low weight.
Yeah, exactly, yeah. Okay, so you take this distribution, and then the nice thing about it is that our set of our set of matrices that we're trying to hit, those that have weights gamma in each row, are kind of likely. So it's a pretty typical set for our distribution on matrices. Okay, and then in order to estimate, so we can use since it's a pretty likely set, we can just use the entropy of this distribution in order to estimate the size of this set of matrices. Okay, and using computations like this, the error can be taken down to just exponential, not double exponential in k, which is nicer. And then, okay, so I won't go into this, but generally you can just use something that's called minimization of relative entropy, also minimization of KL divergence to actually get this explicit formula for F. Okay. One more thing that I can say something about is that I also say that we always have one of these two spaces dominate. So it's either the space of even vectors, or these vectors where u1 equals u2, u3 equals u4, and so on. So these are the two possible dominant spaces. And just like a sketch of how you do something like this. So imagine that there's actually so this so this vector here, this vector space here with the identical pairs of coordinates has many constraints on it, right? Well, the first one has only one constraint, and you can pretty much imagine a spectrum. It's not one-dimensional, of course, but you can imagine a spectrum of all the types of spaces, all these spaces between those that have very many constraints and those that have very few constraints. And then you can ask, okay, so what does this TU function look like? And it turns out that given the, okay, so I'm going to say something very informal, but I'm going to say that given the constraints that you have, the space of your constraints, then this function is convex. Okay, like something a bit more, saying something a bit more well defined is that we only care about spaces here which are direct sums of these VKs, of very simple spaces. Okay, as you can see, this is actually just a direct sum of many V2s, right? So we only care about these, and then our function, and then for a space like this, you can actually use the function f defined before to give to estimate the TU for every u of this form. And then since it's convex, you can see that you get that the optimum has to be in one of these two extremes. Okay, so that's like a very vague idea of how the rest of the argument continues. Okay, and this is pretty much it. Let's just say something about some further open problems. So as I said before, we don't actually know the distribution of x. It would be very nice to understand what this x looks like. And more generally, we'd like to know what the distribution of the whole weight vector looks like. Okay, because we only asked about a specific element of the weight vector. Arguably, this is not the most interesting thing you can ask about it. For example, I guess a more natural question would be not about a specific weight in the weight vector, but about an interval of weights in the weight vectors. And this is what is usually needed for many questions about codes. So maybe you can start by asking about the correlation between two different layers. Okay, so between two different elements of the weight vector. And like, I don't know, a holy grail of this would be to just completely understand the entire weight vector as some random measure. Okay, so what do I mean by looking at it as a random measure? You can just think of this weight. Okay, so you can just normalize this weight vector to be between 0 and 1. And then you can actually think of it as some. Okay, so the code actually defines a measure on a weight. It's basically just the measure that comes from take a random element of the code. What is its weight? And of course, this weight is this measure is very highly concentrated around 1/2. But in code theory, we actually care very much about its its large deviations, because we want our codes to have large distances, and these come from the large deviations of the weight measure, not from the mean. So understanding the large deviations of this random measure in general would be I think would be great if we manage to do that. Okay, and that's pretty much it. Thank you.
Any questions for Jonathan? So if instead of weight distribution, so your last problems on getting more information. Suppose instead of weight distribution, you want distance distribution, but you pick a completely random set. You know, that should be more tractable, perhaps.
I'm sorry,
so
again?
You just pick a random subset of size, whatever, 2 to the 1 minus lambda times n.
Instead of a linear set?
Yeah, completely random set.
Okay.
And then talk about the distance distribution. How many pairs are there at some distance?
Yeah.
Is there better information known?
Yeah, I haven't really thought about that.
Is there any correlational there between?
Yeah, if you take the distance distribution, you do expect to have correlations.
Yeah, I think some higher order things, yeah, I mean. Yeah.
It's like some...
Just because you can't have arbitrary configurations of Hamming. If you take 10 birds, probably you cannot realize every set of Hamming distances. So there's going to be some higher order dependencies once you go to higher moments. Probably even a third moment.
Yeah, I mean, you're still going to have more complex correlations than like the larger the moment you take.
But maybe one could start with just 2, gamma 1 and gamma 2, how the...
Yeah, okay, interesting.
Yeah, without it.
Yeah, okay.
So probably one layer would be just normal, I think. Probably you won't see this case also.
Yeah, of course, yeah, one layer would of course be... Well, of course, yeah, no. No, if you look at one layer even to a very, like, to some high moment, I mean, what are the relations between, I mean, if you have, no, because if you do know that a few of your elements are very close to each other, then it does affect, if you have a few very close elements, and now you have another element, then it being close to one of them means that it also has a good probability of being close to the others, right? So you do get, I mean, so the geometry you have to consider in this case is something like taking intersections of, it would be something with, instead of, here we intersected random, here we intersect linear spaces with spheres, and now we just look at intersections of spheres, not with anything linear. But it's still, you're still going to get some complex behavior in the large order moments, I think. Okay.
Right.
Okay.